In this question 1 then, we're given the same number can be represented in different ways. We have to write 2 more representations of each of the numbers in the table below by choosing only from the following list. So the table below gives us 3 numbers. The first one is 6 to the power of minus 2. So we can do this, I suppose, one of 2 ways. We can kind of work forwards, where we take the 6 to the power of minus 2, mess around with it a little bit and see if we can get to any of the numbers in this list. Or we can take the numbers in the list and then see if we can work our way towards 6 to the minus 2. And the way I suppose I prefer to do it is to kind of do a mix of those two. Starting off with a 6 to the power of minus 2 is a little bit daunting, so I'm going to try and mess around with that a bit and see if I can make it into a number that's a bit more recognizable. So first I'm going to say that 6 to the power of minus 2 is equal to 1 over 6 squared. That's what the power of minus 2 means. It's 1 over 6 to the power of plus 2. So that is 1 over 36. We could say that that is 36 to the power of minus 1, for example. But none of these I can see are in the list. There's a minus 36 there, but that's not the same as 1 over 36, or 36 to the power of minus 1. That's not the same thing. So let's see if we can actually represent that as, say, a decimal and see if we can get anywhere from that. So divide 1 by 36 on your calculator and you will get, say, 0.027777 and a load of 7s. So do we have that there? In fact, we do. There's this one here. Let me mark this in a different color. There's 0.027 with that dot over it. That dot just means that you continue on with that number, so it's 0.027 and then the 7s continue. So there's 1. And what else could we do? We've already tried representing it as a fraction. We could try representing it as an exponent. We could try as a percent. So well let's try a percent then. So to turn this into a percent, multiply by 100, so we get 2.777 and so on percent. Well, that is almost this number up here, this 2.8%. It's not exactly 2.8%, but it does say in the question, and I haven't copied it down, but it says some of the representations may be approximations. So to say that 2.7777 is pretty much 2.8 is just rounding. So we can say that it's effectively 2.8% as well. So we'll move on to the next one then. We have 81 to the power of a half. I don't see any 81s there. There's a 1 over 81, but power of a half does not mean 1 divided by. That's what the power of minus 1 means. Power of a half means square root. So that is the square root of 81, which is 9. So how could we try and represent 9? Well, we could try as a fraction. That would just be 9 over 1. That wouldn't really help us. We could try as a percent. So let's try multiplying by 100 and we get 900%. So just be careful with that because there is a 9% in the list, but that is not the same as 9. That's 0.09. So in fact, the 9 is equivalent to this 900% that we have here. So there's a 900%. So how else could we try and represent this? It's a bit more difficult now. We could try exponents, so that'd be 9 times 10 to the power of 0, but that's not there either. So what else could we do? We know that 9, for example, is 3 squared. Do we have anything that is... Do we have the 3 squared there, or do we have something that looks like 3 squared? Well, we have a root 3 to the power of 4. That's about as close as we can get. So let's see if we can make that happen. So I'm going to say that 3 is root 3 times root 3, and that is squared. Now, root 3 times root 3 is root 3 squared, so we get root 3 squared, and then that's squared again. And our rule for powers that look like this is a to the power of b brackets power of c is a to the power of b times c. So that is root 3 power of 4. So that's what we have. So there's a root 3 power of 4 there as well. So we move on then to the last part, and this is 2 to the power of 20. So let me just scroll down a bit. So we have 2 to the power of 20. And now there's not a whole lot we can do with this other than try and actually evaluate that. So if you put, say, 2 to the power of 20 in your calculator, you're going to get 1,048,576. So do we have anything like that in our list? Let's see. Well, we almost do. We have this 1.05 times 10 to the plus 6. So what we have in our when we evaluated 2 to the 20, we got 1.048 to the times 10 to the plus 6. So if we sort of if we round that, then we'll get 1.05 times 10 to the 6, because we're told that approximations are fine. So let's see if we can find something else that works. What else can we do with this? It's a big number, so we can't really represent it as a fraction. We've already tried to represent it as an exponent, and that worked. We could try trying to represent it as maybe square roots or something like that. But let's go the other direction this time. Let's go through our list and see if we can actually get up to 1 million. So let's say minus 36 is definitely not a million. 9% is definitely not a million. That's 0.09. 1 divided by 9, that is 1 over 9. The fraction is 0.111 and so on. So that's not the same. If we do 1 divided by 62, we get 0.016 and so on, so that's not right either. If we do 1 divided by 81, we get 0.01 and so on as well. So that doesn't count. 10 to the 5 is 100,000, so that's an order of magnitude below what we want. We want a million. This is 100,000, so that doesn't count either. We've already used the root 3 to the power 4, so let's not bother. We got 2 to the 4 times 2 to the 5. Well, let's double check how we combine powers like that. If we have a to the power of b times a to the power of c, then that turns into a to the power of b plus c. So that is 2 to the power of 9, so that doesn't work. The next one, 0.25 to the power of minus 10. We could mess around with that. Let's just put it in the calculator, and we actually get 1,048,000 and so on. So that is our other one. So we said this was 1.05 times 10 to the 6, and it is also 0.25 to the power of minus 10. So you put that in the calculator, those are all equal, and that's the question finished. Now in part B, we're given a number line and we have to work out an appropriate scale. We have to mark the following numbers on the scale. So how do we figure out an appropriate scale? Because all these numbers look a bit different, we don't really know what they are yet. So if we just throw all of these in our calculator, we get this, that root 82 is 9.055, 3 pi is 9.425 or thereabouts, 37 over 4 is 9.25, and 9.3 by 10 to the 0 is just 9.3. So now we know roughly where our scales should be. We know our lowest number in the list is this, the 8.9, and the highest number in the list is 3 pi. It goes from 8.9 up to 9.4 or so. So let's say we go up in 0.1s, then that'll give us a pretty decent idea of where everything should go. So let's say there's 8.9 right there. Then let's say that this is 9, There's 9.1, 9.2, 9.3, and 9.4 is there. So where are all these numbers on this list? Well, we can use the decimal representations that we already have. The 8.9 is already there, so I'm going to just mark that down in red, 8.9. The 9 is already there as well, so there's 9. The next one in our list is 9.055, the root 82, so that's going to be pretty close to 9 there. So there's root 82. The next one in our list is going to be the 37 over 4. That's 9.25, so that is about there. So that's 37 over 4. The next one is 9.3 by 10 to the 0, so that's spot on there. That is 9.3 by 10 to the 0. And so that's 5 out of 6 done. The last one is 3 pi, which is 9.425. That one is going to be right here. So there is 3 pi.